but the root and the soil system are very constrained, which is good because we know them, but they are constrained, so it's not exactly the natural conditions, and there is little interactions between plants. And it's quite a nice place because we can have access to the plant and to the organ levels observations. Opposed to these control conditions, there are the field conditions where the growth is the result of integrating several processes, some of them not very well known, especially regarding root and the soil, which are difficult to assess. There are full interactions between the plants, but we can only access the canopy level and mostly from the top of the canopy, so which are strong constraints. So in this talk, I will mostly focus on the field conditions and to first try to characterize the soil reservoir. So the soil, of course, is very important. It's we need to know the size of the pot as compared to the control conditions where the size is very well known. In natural conditions, it's not always very well known. And we know that the heterogeneity of the soil impacts a lot the capacity to discriminate between genotypes, especially if we don't have any good idea of the available water capacity. Knowing the size of the pot, so the mostly available water capacity of the soil, allows also to quantify the stress. Of course, if we have got other information about the root development, the efficiency of extracting water, and some assumption of the water balance. To get a map of this available water capacity, it's possible to get local samples, soil samples, to extract soil samples from making some holes in the soil to get the local available water capacity, and to try to interpolate over or extrapolate, mostly interpolate, over the whole platform, experimental platform. We can use map of electric resistivity or also maps of previous crops derived from either satellites or UAV observations or even yield maps. And from that, we can get available water capacity maps and assign to each microplots a given value for the available water capacity. This is an example here in Gréoux. Gréoux, it's an experimental site not too far from Avignon, where we have a very detailed map of the available water capacity derived from those previously shown techniques. And here you have the set of microplots. So for each microplot, we can assign a given value of the available water capacity. And because of this knowledge, we can account for the soil heterogeneity by designing optimally the experimental design. So first putting the two modalities, so water stress and irrigation in good places, and then dividing the experiments into blocks. Either here it's two alpha plants, so where we have replicates either on lines and on columns here, in order to reduce the effect of the variability of the available water capacity. But probably more importantly, we can also account for the soil heterogeneity in the data interpretation to try to correct for this variability. This is what has been done here with this model that allows to account for the genotype variability, the modalities, the interactions, the blocks either in line or columns, and also as a covariable, the available water capacity. Actually, we observe here that adding the available water capacity didn't improve that much the accuracy of this experiment because already the spatial model that has been used here to interpret the observations was enough to control the variability. But the question that is posed that probably we can change the paradigm and to try to play with the available water capacity as a modality to try to derive response curves to the water stress over a single experiment. So that was for the permanent characteristics of the soil. Of course, we are interested to monitor the evolution of the water content during the growth of the canopy. So for that, we can set up local soil moisture sensors. And the new things are very interesting that now they can get measurements. We can get the measurements in near real time and then display all the time the values that are measured by those sensors and know exactly what is the status of the experiment in real time. This is at the scale of the microplots. We can do that over a few microplots with electric resistivity tomography. So this is an example here where we calibrated the resistivity as function of the volumetric water content here that show that they are quite good relationships, except maybe for the deep horizon, because we know that these techniques lacks resolution for the deep layers. And we can have, at least here, we have 4 plots with different modalities. And we can see clearly that there are differences between the modalities. So that's a way on few plots to monitor real time the evolution of the soil moisture, so the water balance. And if we want to extend that to all the microplots, we need some kind of modeling where we have to make some estimation of the evapotranspiration according to those, mostly those variables, where some of them are measured, so like the fraction of intercepted radiation that controls the, let's say, balance between evaporation and transpiration, and of course the available water capacity, and with a question mark on the root development and functioning. So this is very interesting approach that needs to be developed probably more than now. Now going back to the aerial parts of the canopy of the crop, there are mostly 2 main ways to assess the impact of the water stress. Either we are looking at short-term crop reaction, so by monitoring the diurnal course of some crop variables, of course, surface temperature, leaf rolling, PRI, I will discuss that later, which is an index that measures the impact of the stress on the balance between xanthophile pigments, fluorescence. And the main constraint when looking at this short-term crop reaction is that, of course, it varies strongly during the day. Because of it's driven by stomatal conductance, photosynthesis, and leaf water potential that, of course, are themselves driven by the radiation, vapor pressure deficit, temperature, winds, all those environmental variables that vary with very short-term time steps. So we need to complete the observations over the whole experiment within few minutes in order to have things that are comparable between the different micropulse. Oppositely, we can also look at variables that result from the integrated crop reaction, mostly variables related to the growth of the crops. So, of course, it's plant height, the green fraction, the green area index, the senescence, fraction of intercepted radiation. We can also look at the organ size because we know that water stress impacts first the growth at the organ level. And what will be very important here is to conduct repeated measurements in order to monitor the evolution of those variables along the seasonal time course of the canopy to understand the establishments of the stress over each microplot. For that, so we need repeated observations with very strong temporal consistency, and for some of those variables with a quite fine spatial resolution, especially if we are looking to the organ size, because we need to look at to identify organs, and to look at the canopy height to get a good value of good accuracy on those variables. So if we are looking to these short-term reaction variables like surface temperature, we'll use aerial systems like UAVs that will be equipped with a thermal infrared camera to measure surface temperature. And generally, we are also using at the same time a multispectral camera to measure the green fraction that impacts, as we will see, a lot the surface temperature seen from the thermal infrared camera. So this is one example here on one experiment 2 years ago in Montpellier over sorghum, where we have two modalities. One is dry modality, so without irrigation. One is irrigated modality. This is time during the day. This is temperature, surface temperature, measured with those hydrothermometers at the ground level. And we see, of course, that the difference between the irrigated treatment that keeps relatively cool because of transpiration is very large as compared to the one from the water stress treatments, where the stomatal conductance is very small, and there is a very small transpiration, and we can get here up to almost 10 degrees difference between the two modalities here. So this is what we observe at the local scale. We can have with the UAV flights the difference over the whole experiments with the irrigated treatment here and the dry treatment here. And we can see also that we have differences between microplots. So these differences are mostly due, unfortunately, I would say, to the green fraction differences between the microplots, because we see, even if we were looking at 45 degrees perpendicular to the row to minimize the effect of the green fraction, anyway, we see quite a lot of soil here, and the soil is hotter than the leaves. So the more soil, the higher the temperature. So this impacts a lot on the temperature measured by the thermal infrared camera. So we have to correct or to minimize for this influence of the green fraction. And one way to interpret that and to correct for this green fraction is to use this trapezoidal representation of the temperature as a function of the green fraction. So here is the bare soil, here is the full cover. So we are somewhere in between. This is a wet situation, and this is the dry situation here. So if we measure the temperature here for a given green fraction, we can compute this water deficit index, the ratio between this distance to this distance. So when it's 0, there is no deficit. When it's 1, it's a full deficit. So this is one way to take into account the impact of this green fraction. The problem is that we have to get those 4 corners. So it's not always easy, especially on the crop, to get a full dry crop cover and the full water cover in good conditions. So that's why probably we need also to use energy balance, but in this case we need to get very accurate measurement of the surface temperature, which is not always very easy. Okay, another short-term reaction is a leaf rolling. So the leaf rolling occurs at the leaf level. It's a change in the cross-section of the leaf that depends on the mostly the potential the leaf potential, leaf water potential. This is some results extracted from the work by Xavier Siro in Australia that shows that we can score visually. Here's the leaf curvature. This is what is usually done in the fields. And we show that it's really strongly correlated with the water potential in the leaf. And when we go to the crop level, we can observe the leaf rolling by changes in the architecture, because even if the rolling is a cross-section process, this impacts the leaf curvature because of, let's say, mechanics in the leaf. So the curvature increases the leaf stiffness, and then you have more erect leaves and, of course, a reduced cross-section of the leaf. This is an example here of the effect of the leaf rolling between the morning and the afternoon, measured with digital hemispherical photography here. So you can see that in the afternoon, there is some kind of opening of the canopy, so more soil exposed to the sun, less leaves exposed to the sun as well. So we can score that visually. That is done currently by breeders, but we can also make measurements of the changes in canopy architecture using these hemispherical photography. And we can see that there is quite a nice correlation between the visual score by the people in the ground and digital hemispherical photography, mostly looking at the fraction of intercepted radiation. We see that there is a very strong correlation between the two. That means that even if the process occurs at the leaf level, the canopy level is largely impacted, and this is what we can see and observe with the new tools like UAV. So this is the score here with time over irrigated treatments. Of course, there is no apparent leaf rolling here, as compared to what we observe over water stress, where we have development of the leaf rolling from the morning to the afternoon. The peak is about 2 o'clock here. And this is scored very well from the visual score and also the fraction of intercepted radiation, with sometimes some discrepancies, but generally it's very, very consistent. So we see that there are strong differences between genotypes, and those differences are mostly affecting the amplitude of the leaf rolling, not that much the evolution during time. Generally it occurs most of the time about at the same time between the different genotypes. So this can be done over a limited set of plots, of course, because it takes quite some time to make those measurements. If we want to extend those measurements to the whole experiments, where you have maybe more than 1,000 microplots, you need to get observations from very high throughput systems like UAVs. And this is what we have done here. So we have used UAVs with a multispectral camera to observe leaf rolling. And this is the correlation coefficient that we get between the visual score by the people on the ground and the estimate from the UAV using this multispectral camera. So we can see that we can get a relatively good correlation, which demonstrate that it's probably possible to score the leaf rolling using UAVs. So we can use also the PRI, which is a proxy of the xanthophil state. So maybe we'll go quickly because I see the time is running. PRI is some kind of vegetation index made with two bands in the green, two different wave bands. It has been demonstrated by Pablo Zarco and many others that there is some relationship with water stress measured by instrumental conductance or water potential in the leaf. But we observe that it's very sensitive to the green fraction. That's a first order effect, the same as for temperature. We also observe that the irritability is not that great. That is the irritability here of this PRI. We can see that PRI is still under discussion. Probably there is some potentials, but we need to correct also for the green fraction at least. Now we can go to the integrated crop protection, like plant height. This can be measured either from the phenomobile, but also from the UAV. From the phenomobile, we can use a LiDAR that provides a 3D point cloud from which we can extract the canopy height. From RGB camera, we can also get a 3D point cloud, so get the Z profile and make quite accurate estimates of the plant height. This is some results here of a LiDAR, but we can get about the same with UAV. We have irrigated treatments here, where we can see that plant height reaches higher values as compared to the water stress treatments. And we can see also that we can have fine measurements, fine enough to be quite sensitive to the available water capacity here, with a range of values here that reflects that is reflected well by the differences in plant height. We have also quite nice irritability, at least for the water treatment. It's not so good for the water stress treatment, mostly because of this variability at the ground level of the water available capacity. It's quite well correlated with biomass, both from LiDAR and UAVs. And as a conclusion here, you can say that canopy height is quite relevant trait. It's quite irritable. It allows to date the start of the stress, and is quite correlated with the biomass, which is a good sign for growth. We can also use a green area index to monitor the growth with a multispectral camera, different bands here. We can estimate by different ways. Here we use the empirical transfer function, so we made measurements at ground and correlated the measurements with UAV measurements. These are the results, shows relatively good performances. And from that, we have also quite a nice irritability here, both on irrigated and water stress. And more importantly, we can try to model the time course to derive other variables. So we have developed some model here that allows to get with few assumptions a good description of the canopy of the green area index evolution with time. And this is some examples here. Evolution of green area index with time on two macro plots, two examples here. You have the two replicates. And this model is quite robust, and it allows to use the parameters as straight and to compute or to derive metrics from GI, like derived slopes, growth or senescence, to get specific dates, like the flowering, for example, or to get integrated values, there's some under the curve of the green area index that are quite also potentials for breeders. If we go to another case, we can also measure the stem diameter. So for that, we need a very fine resolution, like better than 0.2 millimeter, which is possible both for the phenomobile here, it's a fully automatic robot, or from a UAV flying quite low altitudes. And after the harvest, we can have the small stubbers here and try to identify the small circles and measure the diameter of those circles. So this is possible. So this is an extract here of these small circles here. And from that, we can derive the diameter. This is some time. Okay, some results here where we correlated the stem area, so the sum of the area of the small stems per unit area, and multiply that and add the height as covariable to relate the biomass, the areal biomass. And you can see that we have also a quite nice relationship. More importantly, because we have individual values of the stems area, we can have also the distribution of the size of the stems, which is quite potential interest for trying to look at differences between genotypes. Okay. Okay, so we can also try to get the tiering coefficient just by dividing the number of stems by the number of plants that we can get also by the same tools. Those stems, we have seen that, and we have seen also the number of plants. We can get nice estimates with those imaging systems. Okay, so I'm going to the conclusion. So the technology is maturing fast, very fast, I would say. Probably too fast, maybe sometimes. So we have now many measurements that are feasible and quite easily with new vectors, new sensors. We have many new traits potentially relevant for water stress, either for short-term stress reactions, but the interpretation is not so easy beyond the first order because mostly we have to get out the effect of the green fraction. For the integrated crop reaction, we have seen that we have many complementary variables like height, green area index, or other size of organs. We have noticed the importance of the soil heterogeneity, so it's very important to account for that and other environmental variables, of course. And I think now the bottleneck in genetic improvements is of course still phenotyping, but within phenotyping, it's data interpretation. So that's why I say that it's the square of the bottleneck. So it's first bottleneck is phenotyping, and the bottleneck of phenotyping is data interpretation. And this is a big challenge currently to try to get the most from the a lot of measurement that we have got available now. So for that, we need to integrate the repeated measurements into functioning models by combining several observations and dates together. And this integration into functioning models will allow to account for explicitly for the environmental variability and exploit, of course, the knowledge accumulated on the processes. And by using those kind of models, we will provide higher level traits to be used for improved breeding. So I thank you very much for your attention.
Thank you very much, Frederic. Interesting talk.